Okay, I'm sorry for the delay. Let's begin then. So let's start with our next topic, which is mensuration. In mensuration, we will be talking about areas, perimeter, volume, surface areas, all of that stuff. That's what we will be covering in mensuration. Now we have already talked about areas of triangles before, right? So we have seen how to find area for triangle, and that was when we did trigonometry, because trigonometry did involve some questions like that as well. So we understood how to find areas of triangles. So this is what we covered there. There are two formulas that we have: half into base into height. That's one formula for area for triangle. In order to use this formula, you want one side, you take one side of the triangle as the base. Okay, you take one side of the triangle as the base, and then height is the perpendicular coming from the third vertex of the triangle. So if you're using one side of the triangle, for example, this side, then the vertex that is not a part of this side, the third vertex here, the perpendicular coming from that vertex, that's the height, right? And you can find the area using half into base into height using this formula. If it's a right angle triangle, you can just take one of the legs of the triangle as the base, and then the perpendicular to that would be the height. But if it's not a right angle triangle, then you have this choice that out of the three sides, you can take any one of them as the base, and then the height is the line that is perpendicular to that base. Okay, the length that is perpendicular to the base. So that will depend on what side you take as the base. For example, if you have this triangle, if you take the side on the left side as the base, then height would be the perpendicular coming from this third vertex to that side. That's this length 8. Okay. If you have this triangle, then if you're considering this horizontal side as the base, sometimes what can happen is the perpendicular can be outside the triangle as well. This is one such example. If you're considering this horizontal side as the base, then height would be the perpendicular coming from the third vertex, which is this vertex on top, to that base. Now the perpendicular in this case lies outside the triangle. This would be the height, in this case, this vertical length. And we can find the area using half into base into height using the form, using this base and height then. Okay, we can sometimes have something like this as well. If we consider the side on the left side as the base, then the height has to be the perpendicular coming from this third vertex to that base. Okay, again, this can lie outside the triangle as well. Then the second formula is half into AB sine C. Now, when you use this formula, when you have two sides, and the angle between those two sides. When you have this information given, two sides given, and the included angle, the angle between those two sides, you can use the formula half into AB sine C, where A and B are two sides of the triangle, and the angle C is the one that is between those two sides. Okay, this is what we discussed. We looked at a couple of examples in this as well. That's how we find areas of triangles, right? This is one thing that we've done before. In two-dimensional figures, this is one that you will see quite often, triangles, but you will see other types of figures as well. And you would have to find the areas of those figures in 2D shapes. And the second thing that you would have to do would be, you would have to find their perimeter. Okay, so you'll need to find two things for 2D shapes, for two-dimensional shapes. You will need to find the areas and the perimeter. Okay. Now, what does area mean? If I were to show you a diagram, let's say I have a figure like this. Now we'll see how to find the area later on for this figure. It's a parallelogram, right? Area basically is the calculation of the space that you have inside this shape. Area is the calculation of all of this yellow part, okay? It tells you about the space inside this figure, okay? So this is going to tell you something about the space inside the shape. So all of this yellow region, this is the area of this shape, okay? The area covered by this shape. On the other hand, so you can think of it like this, that if I had to fill this figure with ink, how much of ink is going to be used for that? It's everything inside this shape like this, all of this region, you'd have to shade all of this. This represents the area of this figure, okay? The space inside the shape. What about perimeter? Perimeter is the sum of all the outer sides of the shape. Outer sides of the shape. That's the perimeter. Now, in this case, for instance, if you have a parallelogram like this, the perimeter is going to be the sum of these sides. There are four sides that we have. We can call this A, this B, this C, and this D, for instance. What's the perimeter going to be in this case? The perimeter is just going to be sum of all of these sides. That's A plus B plus C plus D. Okay. Now, we will see how to find the area and the perimeter for all of these different shapes that we have. Okay. But that's the idea. Area is going to tell something about the space that is inside that figure. And perimeter is going to tell you about the sum, about the outer boundary of that shape. This is the boundary of the shape. What's the sum of all of those sides at the outer boundary? If you have any line that's inside, for example, you might have a diagonal here of the parallelogram as well. And let's say this is called X. You don't consider X in the perimeter because perimeter only considers all the outer sides. Okay, you just add all of the outer sides of that figure and you get the perimeter. Okay, now we have a number of different 2D shapes, and for those shapes, you will need to find their areas and their perimeter. Okay, now for areas, we have certain formulas that you need to remember. Some of them will be given in the in the formula sheet that you now get in the exam, but many of them will not be given. So for 2D shapes, generally only the triangle formulas are given, and the rest of them you need to remember. Okay, so you need to memorize these formulas for areas. For perimeter, I would recommend that you don't memorize any formulas as such. You just look at what the diagram is, because sometimes it's not some standard diagram. It's a combination of some figures. For example, you might get a figure that looks something like this, that you have a rectangle, and then on top of this rectangle, you might have a shape like this. Now I'll correct that in a moment. My first erasing this part. So on top of the rectangle, what you have is a shape like this. Right now, this is not something that we have a name for as such. Okay, now if you had to find the perimeter of this shape, how would you do that? You would have the sides of this figure. You have one side on the left, one here, one on the right side, although they will be equal to each other, but we have these sides, right? And then we have this arc length here. You would have to add this arc length to the perimeter as well. Let's say this is D. What you would have to do would be, you would have to just add all of these sides, the outer sides. That means this is A, this is B, this is C, and this is D. You add all of them, and that's going to give you the perimeter of the shape. Okay, the outer sides. Now we will not be memorizing any standard formula for this, because now this is a random shape. uh, there can be infinitely many shapes like this, so we can't remember the formula for each one of them. So you'll just remember the definition of perimeter, that for finding perimeter, you just add all of the outer sides of the shape, right? The outer sides of the shape, just add all of them. And what about area? Area is going to be given by the space that is inside that figure. So in this case, you have a semicircle here, kind of. So you can find the area of the semicircle somehow. This space using the semicircle formula. We'll see what that how that would be done. And then you have this rectangle. You can find the area of the rectangle using the rectangle formula. You find both of those areas separately, and then you add them up together to get the total area. Okay, so area is the space that is inside that figure, and perimeter is the length of the outer boundary. Okay. Now, what are the different shapes for which we need to know the area and perimeter the area formulas in particular? Let's start with the first one, which is fairly straightforward. You can have a square. A square looks like this. A square is a figure that has all sides equal and it has all angles 90, right? What's the area formula for a square? Remember, these angles are all 90 in a square and the sides are all equal. Area of a square is given by L squared. So if the side is L, one side is L, then that means all sides are L, right? Area is just L squared. L times L, that is L squared. That's the area of a square. Okay. What about the perimeter? Now for perimeter, all you have to do is just add all of these sides. L plus L plus L plus L. Okay. So in this case, for a square, you get L plus L plus L plus L, and that gives you 4 times L. Okay. Now that's for a standard square. Sometimes what can happen is that one of these sides might be missing, right? So it might be a square, and with that, on the right side, you might have something like this added. How would you find the perimeter in this case? You would say this is the outer boundary of the shape. In that case, for the square part, you would just consider this side, and this side. That's 3 times L and not 4 times L. Plus the sides here, this one and this one. You would not be considering the right side of the square in that case. Okay, so that's why it's generally not helpful to memorize the perimeter formulas, because they will be changing a lot. So it's easier to just look at this figure that you're given and just add all of the lengths that you have in that. Okay, but for a standard square, the perimeter would be just 4 times L. Okay, so that's the first shape, pretty straightforward. Then you have a rectangle. What's the area of a rectangle? Area of a rectangle is given by length into width. So let's say we have a rectangle that looks like this. Now, in this case, let's say one side is L and the other side is W. And of course, their other two sides are going to be L and W as well. What's the area of a rectangle? It's length into width. Okay, so if you want to find the space inside this rectangle, how do you do that? You would just multiply L and W. Okay, that's the area formula. If you had to find perimeter of this shape, what would that be? For perimeter, you just add all of the sides. So that will be L plus W plus W. And that simplifies to 2L plus 2W in this case. But again, as I said, in this case, you can just think of just adding all of the sides and you would get the perimeter like that as well. Okay. Now for triangle, we have already looked at that in a lot of detail before, how to find areas of triangles and perimeters of triangles. So that's another shape that you need to remember the area for. Half into base into height and half into AB sine C. Those are the two formulas that you can use to find areas and that you can use to find areas of triangles. Okay, and for perimeter, you just add all the sides that you have in that perimeter, have in that triangle. Okay, now the next shape is a rhombus. What is a rhombus? A rhombus is very similar to a parallelogram, but it has an additional condition compared to a parallelogram, and that is in a rhombus, all sides are equal. All sides are equal, but all the angles are not equal. So the angles are not 90, but the sides are all equal. Okay, so in this case, one angle is going to be acute and the other angle is going to be obtuse. So they're not 90. If the angles were 90, it would become a square. But if the angles are not 90, this is a rhombus if all sides are equal. Now, how do you find area of a shape like this? One idea is that you break it down into two triangles like this, right? You can do that. You can break it into two triangles like this. Okay. And then if you find area of one triangle, you can just multiply that by 2 because this triangle and this triangle are equal to each other. They're congruent. You can find area of any one of these triangles. So how would you do that? You would say, let's say the base is this horizontal side. If you take this side as the base, then what would the height be? The perpendicular coming from the third vertex, this would be considered the height of this rhombus. And you could say the area of the triangle is given by 1/2 times the base times the height. That's the area of this triangle on the right side of this rhombus. You multiply this by 2, and that will give you the area of the complete rhombus. So multiply this whole thing by 2. What happens when you do that? 2 and 2, they get cancelled, and you're left with just base into height. Base times the height. That's what the area of a rhombus is given by. Area of rhombus is base times height. And again, just like for a triangle, the base and height are perpendicular to each other. In this case as well, when you take one side of the rhombus as the base, then height is going to be the perpendicular coming from the other side, from the opposite side to the base. That would be the height. Height will always be perpendicular to the base. Okay. So if you want to use this formula directly base into height, you don't even need to break it down to triangles. You can say, okay, if you have a rhombus that looks like this, you can take one side of this rhombus as the base, and then the height would be the perpendicular coming from the opposite side to the base. This would be considered the height, and you can find the area used in this. Okay. Now, rhombus is actually just a particular kind of parallelogram. It's a special type of parallelogram. So this formula that we just discussed, it works in general for any parallelogram as well. So you can have a shape like this, for instance. Let's say you have a parallelogram instead, and that looks like this. For a parallelogram as well, you can consider any one of the four sides as the base. So if I consider this side as the base, what about the height? Height is going to be the perpendicular coming from the opposite side to this base. So this might be the height, right? You can make that perpendicular anywhere since the opposite sides are parallel. You can measure that perpendicular from anywhere and it'll be the same. So if this is the height, then the area formula for a parallelogram is the same as well. That's base into height. Area of a parallelogram, that's also base times height. And if you think about it, all of these four shapes, they kind of have the same formula because you can argue that rhombus is a particular kind of parallelogram. Rectangle is also a special kind of parallelogram. Its opposite sides are parallel, so it satisfies the condition for a parallelogram. Square is also a special kind of parallelogram. Opposite sides are equal and parallel. So for all of them, we can actually use the same formula, base into height. Consider any side as the base. Height is perpendicular to that. In a square, since both of them are equal, both sides, base and height, we can write that as L squared as well. For a rectangle, you can consider one side as the base and the other would be height, and that will be length into width or base into height. That's the same thing as well. For a rhombus and parallelogram, we specifically use the words base and height because uh, this comes from the area of the triangle. So using the area of the triangle, we can just dividing this rhombus and parallelogram into two parts like this, and then finding the area of one triangle. We can just multiply that by 2, and that gives us this formula for the rhombus directly, which is base into height. And similarly, for the parallelogram, which is also base into height. Okay, now again, these are not given in the formula sheet. You will need to remember them. This is how we find the area of a parallelogram, base times the height. Okay, next shape. For perimeter, remember, you just have to add all of the sides. For perimeter, you just have to add all the sides. All right. So we're not writing any formulas for that. You can figure it out on a case-by-case basis. Whatever is the outer boundary, you add the lengths of all of those sides, and that will give you the perimeter. What about trapezium? That's another 2D shape that you have. Area of a trapezium. Okay, what does a trapezium look like? A trapezium is a shape that has two sides parallel, but then the other two sides, they're not parallel. So in a parallelogram, opposite sides, both the set of opposite sides are parallel. But in a trapezium, only two sides are parallel and the other two are not parallel. So it might look something like this, for instance. This is one possible trapezium that you can have. How do you find the area of this trapezium? The formula for area of trapezium is given by 1/2 into sum of parallel sides times height. What's height? Height is the distance between the parallel sides. Height is the perpendicular distance between the parallel sides. Okay, now what do we mean? What do we mean by this? Let's consider this trapezium. Which two sides are parallel? The horizontal sides in this case. These two sides are parallel, right? Now we can say one of these parallel sides has length A and the other has length B. What about the height? Height is going to be the perpendicular distance between these two sides. We would say this is the height of the trapezium. Okay, so in the formula, we could have something like this then. So the general formula is 1/2 into sum of parallel sides multiplied by height. For this particular trapezium, we could say the area can be given by 1/2 sum of parallel sides. What are the parallel sides? A and B. So we can say it's going to be A plus B times height for this particular diagram. Okay. Now trapezium is not always going to be like this, that you have two horizontal lines, two parallel lines like that are horizontal. It could be tilted as well. It could be in a vertical direction as well. For instance, a trapezium that is on another orientation, it might look something like this, for instance. Okay, so let's say we have a figure that looks something like this. Okay, this is also a four-sided figure. This is also a four-sided figure. But now the parallel sides are vertical like this. These two sides are parallel. If two sides are parallel and the other two are not parallel, we say this is a trapezium. Okay. How do you find the area of this trapezium? Sum of parallel sides. What are the parallel sides? You can call this side A, this side B. And then the height is going to be the perpendicular distance between those two parallel sides. So height is not necessarily vertical always. It can be horizontal like this. The idea is it should just give you the distance between the parallel sides. Okay. So in this case, this distance, let's call that h. Then this would be the formula that you have for the area of this trapezium. So trapezium can be in both orientations. It could be horizontal, it could be vertical like this as well. Okay. So you need to be able to find area of trapezium that's given by 1 over 2 into sum of parallel sides times the height. Okay. All right. Then a lot of questions involve calculations involving circles. Now, what about circles? What's the formula for area of a circle? If you have a circle like this, area of a circle is given by pi r squared. Okay, what does area tell you? Area tells you the space inside the circle, right? That's the area of the circle. Now, this is one thing for which you do need to remember the perimeter formula because otherwise you cannot figure it out yourself. Perimeter of a circle, that's basically the circumference of the circle. This is the circumference of the circle. Okay, this is the boundary of the circle, right? This is known as the circumference. This curved part of a circle, it's known as the circumference. And it's given by 2 pi r. And if you have a circle like this and you have to find the perimeter of the circle, what's the definition of perimeter? That you're looking at the sum of all the outer sides. There's only one outer side here. There's only one side, in fact, and that's this curved side. What's this? What's this? What's the length of this side? That's 2 pi r. You would say the perimeter of a circle like this is equal to 2 pi r. Okay. So perimeter of a circle is given by 2 pi r. Now, in a circle, you have to do a lot of other calculations as well. Like you might have to find areas of sectors inside a circle or areas of segments inside a circle. How do we do those calculations? Let's talk about that now. Areas of sectors, areas of segments, and similarly, perimeter of sector and perimeter of segment. Let's talk about that now. So let's say we have a circle like this. We're going to talk about sectors first of all. In this circle, let's say the center of the circle is here. This is the center of the circle. Now, if I have lines going or radius of the circle going from the center to any part of the circumference like this, if I have two radii like this shape that I get from this shape is called a sector. The shape is called a sector. So this yellow part here, this is a sector. Okay. This is a sector. The remaining part, this part, that's also a sector. That's the bigger sector in the circle. And there's a terminology that we use here. The bigger sector, we call that the major sector. And the smaller sector, we call that the minor sector. So this is the major sector that we have here. The green one. This is also a sector. So sector can have both of these shapes. We have a major sector and a minor sector. Now remember, a sector always has three sides. A sector always has three sides. It always has three sides. Two of them are the radii of that circle. Plural of radius is radii. So we have one radius here, another radius here. Okay. And then the third side is the arc. Okay. So you can see in any sector, you would have three sides. You'd have three sides. Two radii and one arc. So if I were to split it into two parts, it would look something like this. A sector can be any one of these shapes. Though, so on the left side, I have a major sector. All right, this green one is the major sector. And this yellow one is the minor sector. And this is the minor sector. How can we find areas and perimeters of these sectors now? That's the question. So we already know how to find the area of a circle, but what about area and perimeter of these segments? So we can have a minor sector like this, or we can have a major sector like that. Both of these are sectors. Remember the formula for the area of a circle? Area of a circle is given by pi r squared. Okay, that's the area of a circle. Now that gives us this complete region inside the circle, all of this region, right? However, we are interested in, let's say, only this green part or the yellow part. For this green sector, what's the angle of this sector? What's the angle of this green sector? This is the angle. So at the center, you have this angle. We call this angle theta. And for that smaller sector, this is the angle at the center. We call this angle theta as well. Okay. Now, you see, the total area of the circle is given by pi r squared. All right. What's the total angle in a circle? It's 360 degrees. Complete angle in a circle is 360 degrees. Yeah, complete angle in a circle is 360 degrees. What proportion of that is in any of these two sectors? So for example, let's assume that this angle was 280 degrees, or maybe, yeah, 280 degrees. That's this angle theta. Now for a complete circle, the area is given by, for the complete circle, the area is given by pi r squared. But in that complete circle, the angle is 360. If we only want area for the part where the angle is 280, what we do is we calculate proportion of that what proportion of the total circle are we considering? 280 out of 360. So the area of this sector is given by 280 over 360 times pi r squared. And that will give you the area of this sector. Similarly, let's suppose this angle here was 80 degrees. What about the area of this sector? Now, the area of the complete sector is given by pi r squared, right? What's the radius? This length here and this length here, these are the radii. Area of the complete sector is given by pi r squared. A complete circle is given by pi r squared. What proportion of that complete circle is in this sector? Complete angle is 360. This is only 80. So what we can do is we can say it's just 80 out of 360. So this is the proportion that we have for area as well. So we multiply this by pi r squared. So from this, we actually have a general formula for area of a sector. And that looks like this: theta over 360 times pi r squared. Okay, for any of these shapes, major sector, minor sector, it doesn't matter which one it is. The formula is the same. It's just that in a major sector, the angle is going to be more than 180, and in a minor sector, the angle is going to be less than 180. But in either case, the formula is the same because you're just calculating the proportion of the whole circle that is contained in that sector. All right. So that's the area formula. That's one thing that we need to know for sectors. Then the other thing is the arc length. So for the major sector, for instance, this is the arc length that we have. Okay, this is the arc length. The arc on the side. This is the arc. How can we find the length of this arc now? We use the same idea that we used for area. And we do something like this. We say, okay, for a complete circle, the arc length is given by 2 pi r. We saw that above. Perimeter of a circle, the circumference of a circle, that's given by 2 pi r. What proportion of that is contained in this sector? What proportion of that is contained in this sector? So complete arc would have been like this, right? But in a sector, there's only some portion of that included. What proportion is included? The angle is 280 here. The angle of a complete circle is 360. So if we had to find the arc length in this case, just like area was 280 over 360 times pi r squared, the arc length would be 280 over 360 times 2 pi r. So you just calculate the proportion of the circumference that is included in this sector. In the second case as well, you would say the arc length is given by 80 over 360 times 2 pi r. So that's where this formula comes from for the arc length, which is theta over 360 times 2 pi r. For the complete circle, the arc length is 2 pi r, and you're just calculating the proportion of that that is included in a particular sector. So area of a sector and arc length of a sector, these are formulas that you now need to remember. Arc length of a sector is given by theta over 360 times 2 pi r, and area of a sector is given by theta over 360 times pi r squared. Okay, I hope that makes sense. That's how we find area and arc lengths of these sectors. Okay. Now another problem is, how do you find the perimeter of the shape? So we talked about the arc length, we talked about the area. What about the perimeter? So let's talk about the perimeter of the first shape. If you have this shape, and in this shape, we are saying that the angle is 280 degrees. So we have a shape like this, and the angle is 280 degrees. What if we had to find the perimeter of the sector, given that the radius of the sector was, let's say, 4 units. This was 4 centimeters or 4 meters or whatever. But the number is 4. The radius is 4. How do you find the perimeter of this? And the arc length of this? And the area of this? The area formula is going to give you the area of the sector. What's that going to be? What's the area formula? Theta over 360 times pi r squared. Theta is 280. Divide that by 360 into pi r squared. And that gives you some value. You can see what that is. Radius is 4 in this case. We'll say it's pi into 4 whole squared, and that will give you a result. Okay. Similarly, for arc length, what you can do is 280 over 360 times 2 pi r. 2 pi into radius, which is 4, that is going to give you the arc length as well. Let me quickly do these calculations. 280 divided by 360 times pi r squared. So that's pi into 4 squared. And that's giving me 112 over 9 pi in decimals to 3 significant figures. That becomes 30.1. What about the arc length? The arc length is given by 280 over 360 into 2 pi r, 2 pi into radius, and that's giving me 19.5. That's the arc length that we get in this. Now, what about the perimeter? Now, since we're going to use this in the perimeter as well, what I'm going to do is I'm going to write a more accurate number here first for 5, 4, 8, let's say, and then we can round it off to 19.5. And then for the next calculation, I can use this more accurate number so that my answer turns out to be accurate. What if I had to calculate the perimeter of this? Perimeter of this shape. What's the definition of perimeter? It's the length of the outer boundary, sum of all the lengths of the outer boundary. What's the outer boundary of this shape? We've got this radius, we've got this radius, and we've got this arc length. Right? Now we have already found the arc length. The arc length is 19.548. So that's one thing that we would be using in arc length, 19.548. But not just that. Remember, the sector has 3 sides, 2 radii and 1 arc. This is just 1 arc. What about the radii? This side is 4, and this side is also 4. So we add to it 4 and 4, and that gives us 27.5. That's the perimeter of the sector. And similarly, you can do it for a minor sector as well. It's the same thing. We just add the 2 radii and the arc length. That will be the perimeter. Okay, so make sure that you understand the difference between the arc length and the perimeter. Arc length is just this curved length. Perimeter will also include the 2 radii. All right. And then finally, for sectors, you need to know about, for circles, you need to know about this shape called a segment. Notice the difference between the two shapes. This was a sector where we had 3 sides in total, 2 radii and 1 arc, right? A sector always has 3 sides, in which 2 of them are radius and 1 is arc length. What about a segment? What if we had to find area of some segment? How can we do that? What can a segment look like? Let's say we have a circle like this, and the center of the circle is here. If you have any chord in this circle, let's say this chord divides this circle into 2 parts. Both of them are segments. So this shape that you get on one side of this straight line, one side of that chord, this is a segment. We call this a minor segment. It's the smaller segment out of the 2. And the remaining part, that's the major segment. Okay. This part is the major segment. Both of these shapes are known as segments. All right. Now, a segment only has 2 sides. Segment only has 2 sides. What are those 2 sides? One of them is a chord, and the other one is an arc. Okay. One of them is a chord, and the other of them is an arc. Okay. Sector has 3 sides. 2 of them are radii. Okay. Now, how do you find area of a segment? How do you find perimeter of a segment? For perimeter, you would just add the length, the arc length, and the length of the chord. But what about the area? How do you find the area of these 2 segments? Okay, let's think about the major segment and the minor segment, both of them separately, and see how we can do that. Let me draw it on the side again now. So let's say we have a segment that looks like this. So we're talking about the smaller segment first of all. We have this circle in which, let's say, there's a line that goes like this. And this is the area that we are looking for. We want to find what this area is. Okay. And what information do we have? We know that the radius of the circle is, let's say, 6 units. That's one piece of information that we have. And the angle that we have got here, this angle, let's say this angle is 105 degrees. These are 2 pieces of information that were given. And what we are interested in is finding the area of the segment. Area of the segment. Now remember, this is a minor segment, right? This is a smaller segment. Area of this minor segment. How can we do that? We know the area of the sector already, right? We know the area of the sector already. What's the area of a sector? Theta over 360 into pi r squared. So that will be this complete shape. This is a sector, right? What we can do is we can find the area of this whole shape, area of sector, and we can subtract from that the area of this triangle. And that will give us that shaded part. So we don't have a direct formula for area of a segment, but we can do it like this. We can find the area of the whole sector. So basically this shape, this is a sector, right? Subtract from that area of the triangle. Okay. Let me name it something. Let's say this is O, this is A, and this is B. So the idea would be to find the area of the segment. We say it's going to be the area of the sector Okay, can you still hear me? Can you still see my screen as well? Okay, I think I got disconnected for a minute or so. Okay, all right. Area of a minor segment, what is that given by? That's area of sector, which is OAB in this case. Area of sector OAB minus the area of the triangle OAB. That's how we can find the area of the sector. What does that turn out to be? Area of the sector, that's theta over 360. Theta is 105 divided by 360 times pi r squared. So that will be pi into 6 squared. That's the area of the sector. Subtract from this the area of the triangle. How do you find the area of this triangle? We're talking about this triangle. How can we find the area of this triangle? We have 2 formulas for area of triangle, right? Half into base into height or half AB sine C. Now in this case, since we know 2 sides already, we know one is 6 and the other side is also going to be 6 because they are both radii. So we have 2 sides in this triangle and we have the angle between those 2 sides. We can use that sine formula for the area of the triangle, half AB sine C. So half into 6, the product of these 2 sides, into sine of the angle between them, which is 105 degrees, And that should give you the result. You can see what this is. That will be the area of this segment. Okay. So if you have to find area of this minor segment, this is how you do it. You find the area of the sector and subtract from that area of the triangle. And that gives you that required region. Okay. Now, sometimes you might have to find area of a major segment. Okay, you might have to find area of a major segment. Now, what does that mean? You might have a figure that looks something like this, that you have a circle. And let's make a major segment out of this. Let's do it like this. So we have a shape that looks something like this. Now, this circle will have its center somewhere. Let's say that's here. And you want to find all of this shaded region. You want to find all of the shaded region. How can we do that? How can you find the area of this whole shaded region? This is a major segment. It's coming from a circle, right? So we have gotten rid of this part of the circle, and we're only considering this shaded part. How do you find the area of this segment? Now, this is called a major segment. We don't have a formula directly for this. Again, what we can do is, sorry. Again, what we can do is we can find the area of a sector and area of a triangle to find this shaded region as well. This is a major segment now. Okay, now how can we do this? Let's say we are given that the radius of this circle, radius of the sector, that is some number, let's say that is 8. And we're given this angle. Let's suppose this angle is 100 degrees. That's the information that we have. And what we want to do is we want to find the area of the segment. Now, this is a major segment. Area of the major segment. Now, how do you divide this figure now so that you can find the individual areas and then you can add them together? This is a segment, right? We can think of it like this, that we have one sector. This part, this is a sector. This is a major sector, right? We can find the area of that sector. And then add to that the area of this part, which is a triangle. So in the previous example, when we had to find the minor segment, this yellow region, we found the area of the sector and we subtracted from that area of the triangle because we had to exclude this triangle from that area. But now in this case, if you have to find this whole region, all of this region, how would you find that? You would find the area of this yellow sector and add to that the area of that green triangle. So area of the major segment, that is given by, let me again label these sides like this. Let's say this is O, this is A, this is B. Area of this major segment is given by area of the major sector, right? That yellow sector, that area, plus the area of the triangle, which is triangle OAB. So we would have to add both of these areas together. The green one, that's the area of the triangle, and the yellow one, that's the area of the major sector. Okay, now how can we do that? Area of sector, what is that given by? Theta over 360 into pi r squared. Theta over 360 into pi r squared. Now, what's the theta? What's the angle? Remember, we're talking about this yellow region. We're not going to use angle 100 here. The angle of this sector is basically this angle here. Okay, this angle. What's this angle? Complete circle is 360 degrees. 360 minus 100. This angle would be 260 degrees. So for the angle of this sector, you would actually use 260 degrees. And then pi r squared, Radius in this case is 8. So we can input 8 here. That's the area of this major sector. And now we add to this area of the triangle OAB. How do you find the area of the triangle? Again, we have two sides. One side is 8. The other side is also 8 because that's also radius. And we have the angle between them. Area of the triangle is given by half AB sine C, half into one side, into the other side, into sine of the angle between them, which is 100. And that should give you the area of this major segment. And put this on a calculator, find the result. That's the area of this whole sector. Make sense? Any problems with this? Okay, so we talked about the areas and perimeters of these 2D shapes that we have. For perimeters of these sectors and segments, you would just find the length of the outer boundary. That will be the arc length. And in case of a segment, it would be chord as well. You can find the length of the chord using trigonometry. So if you have two sides here and the angle between them, it's easy to find the third side, right? You can find that third side and then this arc length as well. And that you can add those two things together to find the perimeter of the shape as well. So perimeter is just found by adding all the lengths in the outer boundary. Okay. But for areas, you need to remember these formulas. Now, let's have a look at one quick example before we end for today. Let me see if I can find one quick one. Now, you can try these questions. Let me know the problems that you have, and we could discuss them in the next class then. Okay, let's try this one. This is this also requires symmetry. Okay, let's try this quickly. This looks a bit complicated. Is it related to the first part? Okay, sorry, it's related to the first part. This is again symmetry. Okay, so this basically tests these things that we've just done right now. Let's do this quickly and see if we can do it. The diagram shows a major segment of a circle with center O and radius 15 centimeters. A and B are 2 points in the circumference such that AOB angle is 60 degrees. Find the area of the major segment. So basically, we want to find all of this area. How can we do that? Find the area of the sector and add to that the area of this triangle. Okay, what's the area of the sector going to be? You first of all find this angle. What's this angle? 360 minus 60. This angle is 300. Area of the major segment, area of this whole segment, that's going to be area of sector, the major sector, plus the triangle. And that's what this area is going to be. What about the sector? Theta over 360. That means 300 over 360 times pi r squared. What's the radius? Radius is 15. That will be pi into 15 squared plus the area of the triangle. This triangle, how can you find the area of this triangle? This is 15. This is 15. The angle between them is 60 degrees. So that will be half into 15 into 15 into sine of 60. And that will give you the area of this whole segment. Okay. You just add these up and you get the result. It's from the calculator papers. You can put this on a calculator. I would recommend that you do these calculations separately. Evaluate this separately, then evaluate this, add them up together, and you get the result. And that's 4 marks, fairly straightforward. Perimeter of the major segment. Okay, now that's interesting because we haven't talked about this as a formula, right? So how do you find the perimeter now? Perimeter of this major segment. Perimeter means the length of this outer boundary. So this is the outer boundary. That's the arc. And this is the outer boundary of the shape, this arc. And this side. We have to add these two sides. Now, arc length is easier. Let's find that first. What about this arc, first of all? Can we find this arc? Arc length, that is equal to 300, right? The angle is 300 over 360, theta over 360 into 2 pi r 2 pi into r. What's r here? R is 15. That will be the arc length. That's one thing that we are looking for. Okay, so we'll find this from your calculator and see what that gives you. Theta over 360 into 2 pi r. And then what about this base of the triangle? How do you figure this out? Well, if you think about it, this angle is 60 degrees. This angle is 60 degrees. And these two sides are equal to each other. This is 15 and this is also 15. That means it looks like an isosceles triangle, right? It's an isosceles triangle. Why? Because two sides are equal. This is radius, this is radius. That means the sides that are opposite to the angles that are opposite to these sides are also going to be equal. So this angle here and this angle, they're going to be equal to each other. Okay, now what are those angles going to be? If this is 60 degrees, the remaining angle is 120, right? 180 minus 60. The remaining angle is 120. Divide that by 2. And that gives you each of these angles is 60 degrees as well. This is 60 and this is 60. Now that tells us that all the angles are the same. That means this triangle is actually an equilateral triangle because all the angles are equal to each other. Okay. Now, if it's an equilateral triangle and the other two sides are 15, that tells us that this horizontal side here is also going to be 15. This is also 15. So we can just add that 15 to this arc length, and that will give us the perimeter. We can do it quickly. 300 divided by 360 times 30 pi, and that's 25 pi, which is 78.54. And then the perimeter is going to be 78.54 plus that 15, and that's 93.54. In your final answer, you would write 93.5. That's the perimeter. Okay, that's the arc length plus 15. That's the perimeter. Okay, now it says, shape 1 is formed by joining this segment to a trapezium. So now we have a trapezium added to this shape. Along AB, so you can see that in the figure. AB is parallel to DC. DC is 25 centimeters, and the perpendicular height of the trapezium is h. The area of the trapezium is 248 centimeters squared. Calculate h. So we're given the area of the trapezium. Okay, area of trapezium is given. Now, what's the formula for area of trapezium? Is my screen stuck? Or is it fine? You can see my screen rotating, right? Scrolling down. Okay, all right. Now the area of trapezium is given to be 248. How do you figure out the length h, the height of the trapezium? That's h. Now what's the area of a trapezium? Area of trapezium is given by 1/2 into sum of parallel sides into height. That's h in this case. Now they're saying that the area is 248. Take care of the units, centimeter squared, and these are all centimeter. Okay, so that's okay. The units are the same. That's not a problem. 248, that equals 1/2 into sum of parallel sides. This side we know is 15. So 15 plus 25 times h. And we can find the value of h from this. On the right side, we have 40/2 times h. On the left side, we have 248. This cancels out to give you 20, 248/20. That will give you the value of h. You can see what that is. 12.4. That's h. That's the height of that trapezium, 12.4. And that's what we were looking for. Okay. Now, this is another thing that they do sometimes, that they use the similarity concepts here as well. We will talk about this in the next class as well. What happens when you have similar figures? But let's do this since we're doing this question already. Shape 2 is geometrically similar to shape 1. Shape 1 was this, shape 2 is this. These are similar shapes. The longest side of the trapezium in shape 2 is 5 centimeters. Okay, so this is 5. In the previous shape, it was 25. These are similar figures. Find the radius of the segment in shape 2. What's the value of r? Now, in similar shapes, corresponding sides have the same ratio, right? So we have radius here and we have 5 here. What's the ratio? We can say the ratio is r over 5 between these sides. Okay. Radius in the numerator and this side in the denominator. Do the same thing for the other figure. Radius in the numerator, that's 15. That longest side in the denominator, which is 25. These ratios should be the same, right? Ratios of corresponding sides, they should be the same. R over 5 should equal 15 over 25, right? Or another way to think about this could be R over 15. So you could do R over 15. And then you can say that should be equal to 5 over 25. That's the same thing as well. That's equivalent. These two are equivalent statements. You can do it either way. And that will give you the value of R. R equals 75 over 25. That turns out to be 3 in this case. This is 3 centimeters. All right. Then they ask you to find the total area of the shape 2. The total area of the shape 2. Okay. How can we do this? Similar figures. This is the rule that we have for them, right? Area of one figure divided by area of the second figure. This ratio, the ratio's areas, that's ratio of the areas is the same as the square of the ratio of their lengths, right? That's the rule that we have for similar figures. Do we have the area of that first shape? Well, we found the area of the major segment earlier. Well, we did not actually evaluate it. Let me do that quickly now. 300 over 360 times 15 squared times pi plus, I would recommend that you do it separately. This is more prone to errors, what I'm doing here. Sine of 60. Look at my calculator. Gradient model is correct in that. Okay, so this is giving me 686.48. And that rounds off to 686 to 3 significant figures. This is 686 centimeters squared. That's the area of that segment. Then they gave us that the area of the trapezium is 248. Let's use that here. One area, the area of that first figure, we can say that is 648.48. That was the area that we got for that major segment, plus the area of this trapezium, that was 248. So area of that complete first shape, that was 934.48. Area of that complete first shape. Okay, that's 934.48. All right. Now, do we have the ratio of their lengths? Do we have the ratio between their lengths? So if this is 5, this is 25. So we take one length from here, one length from there, and that will give you, so we're calling the first one shape 1 and this shape 2. So we can say this is L2. L2 is equal to 5 and L1 is equal to 25. Let's put that here in this formula. A1 is 934.48 divided by A2. That's what we are looking for, the total area of the shape 2. That should equal L1, which is 25, over L2, which is 5, whole squared. And that should give us the value of A2. You can see what that is. 934.48 divided by A2. That equals 25 over 5 is 5. And then 5 squared is 25. On the right side, we would just be left with 25 when you evaluate this. Right? That's 5 squared, that's 25. And then you can find the value of A2, that's the second area. That will be this number divided by 25. And that's 37.379. Rounded off to 3 significant figures, that would be 37.4. That's the area that we were looking for. Okay. Does this make sense? Any problems with this? Any questions on this? Make sense? Okay, so tomorrow we will be doing 3D mensuration. I'll be uploading this worksheet. You can practice from this. And then tomorrow we'll cover the concepts of 3D mensuration. So over the weekend, then you can complete the worksheets. Um, that means at least do like 10, 15 from each worksheet. And then if there are any problems, we can discuss them later on. That's it for today. Today, I'll see you again in the next class. I'll also be asking you about the updated time for Ramadan on WhatsApp. So there are two possible slots that we have for that. I'll post that in the group and you can respond then, inshallah. Okay, so that's it. I'll see you again in the next class. And that's this.